Right now, every kilogram humanity sends to Mars costs roughly $22,000. And almost all of that money is burned as chemical fuel escaping the one celestial body we have already reached, the Moon. Sitting just 3 days away, the lunar surface is loaded with aluminum, titanium, oxygen locked inside its rocks, and enough helium-3 to theoretically power Earth for centuries. Yet we treat it like a layover, a place to plant flags and leave. NASA does not intend to leave again. Buried inside a 214-page architecture study updated as recently as 2024, there is a proposal that reads less like a space program and more like a transcontinental railroad project, a mass driver, an electromagnetic launch track stretching 1,000 kilometers across the lunar surface, capable of hurling 10-ton cargo pods to Mars orbit, to Earth orbit, to the moons of Jupiter, without burning a single drop of fuel. No rockets, no combustion, just raw electromagnetic force, a frictionless sled, and a rail that never ends. This is how they plan to build it. Before a single rail segment is laid, the track needs a home, and not every stretch of the Moon qualifies. The selection team narrows the candidates to a region along the lunar equator, specifically a corridor skirting the southern edge of Oceanus Procellarum.
I have seen the blueprint. NASA's plan for a lunar launch track is no longer a dream.
The ocean of storms. The equator matters because launching eastward from it adds the Moon's own rotational velocity to the cargo, roughly 4.6 meters per second. That is free energy baked into geography. The terrain here is basaltic flatland, ancient lava flows that cooled billions of years ago into some of the smoothest real estate in the solar system. But smooth is relative. At the scale of a 1,000-kilometer rail, even a 2-meter boulder becomes a crisis. So the first machines to arrive are not builders. They are surveyors, a fleet of autonomous LiDAR rovers that spend 11 months mapping every ripple, every buried crater rim, every subsurface lava tube within a corridor 40 meters wide and 1,012 kilometers long. Each rover drags a ground-penetrating radar sled behind it, pinging ultrasonic pulses into the regolith to build a three-dimensional density map of the soil down to 9 meters. The data streams back to a relay satellite parked in a halo orbit around the Earth-Moon Lagrange Point 2, where it is compiled into the single most detailed topographic survey ever made of another world. That map becomes the blueprint. The foundation is not concrete. Concrete requires water, and water on the Moon is far too precious to pour into the ground. Instead, the track sits on a sintered regolith bed, lunar soil heated to just below its melting point by microwave emitters mounted on slow-crawling robotic platforms. The microwaves vibrate the iron-rich particles in the regolith until they fuse into a ceramic-hard slab without ever becoming liquid. Each platform processes a strip 3 meters wide and 4 centimeters deep, moving at roughly 60 meters per hour. Behind it, the soil that was powder an hour ago is now a rigid, load-bearing surface, stronger than most asphalt on Earth. 44 of these platforms work in parallel, leapfrogging each other in a continuous chain that stretches back to the horizon. At peak output, the sintering line advances 1.2 kilometers per day. That means the foundation alone takes over 2 years. 2 years of robots crawling in silence across a gray wasteland with no atmosphere to carry the sound of their work. Just the faint vibration through the ground if you pressed your glove to the surface.
Precision isn't a recommendation here. It's a matter of absolute survival for the track.
While the foundation cures, the rail fabrication begins inside a pressurized manufacturing habitat, positioned at the track's origin point, Base Camp Meridian. This is not a small outpost. Meridian is a cluster of 7 interconnected inflatable modules, shielded by 3 meters of piled regolith, housing a crew of 18 and a foundry that would make a terrestrial steel mill engineer uncomfortable. The raw material is ilmenite ore, the most abundant iron titanium oxide on the lunar surface. Robotic scoop loaders haul it from a nearby quarry pit and dump it into a solar thermal concentrator, a parabolic mirror array that focuses enough sunlight to melt rock at 1,600 degrees Celsius. The molten ilmenite is chemically reduced inside an electrolysis chamber that strips the oxygen away. That oxygen is captured, compressed, and stored as breathing air and future rocket oxidizer. while the remaining iron-titanium alloy is cast into 6-meter rail segments using a continuous pour mold. Each rail segment weighs approximately 310 kilograms in lunar gravity. On Earth, that same segment would weigh nearly 1,900 kilograms. This weight difference is not a convenience. It is the entire reason building this on the Moon is possible. The rail is not a simple beam. Each segment is a dual-channel linear synchronous motor track, 2 parallel rails separated by a 40-centimeter gap, with embedded copper alloy coils wound at precise intervals along the inner faces. When electric current pulses through these coils in sequence, they generate a traveling magnetic wave, essentially a magnetic hand that grabs the cargo sled and shoves it forward. Then the next coil grabs it, shoves again, and so on, thousands of times per second. The sled never touches the rail. It floats 6 millimeters above the surface on a magnetic cushion, eliminating friction entirely. No friction means no speed limit imposed by contact. The only limit is how much electromagnetic force the coils can sustain. The design spec calls for a terminal velocity at the end of the 1,000-kilometer track of 2.4 kilometers per second. That is 8,640 kilometers per hour. That is fast enough to place a cargo pod into a low lunar orbit without any onboard propulsion at all. Laying the rail is a ballet of robotic precision. A transport rover carries 20 segments at a time, from meridian along the completed foundation. At the railhead, a placement gantry lifts each segment, aligns it using laser interferometry accurate to 11 microns, and locks it to the previous segment with a friction stir weld, a process where a spinning tool plunges into the joint and plasticizes the metal without melting it, creating a bond stronger than the parent material.
With this turnaround time, we're redefining what's possible. Look at this, fresh off the launch, already preparing the next one.
Behind the gantry, a second rover unspools superconducting power cable from a drum the size of a small car, burying it in a shallow trench beside the rail and connecting it to each coil cluster. Every 50 kilometers, a solar power substation is erected. An autonomous unit that unfolds its own panel arrays, locks into the buried power trunk, and begins feeding the grid. The track is not powered from one end. It is powered from everywhere, a distributed energy network with no single point of failure. If substation 37 goes dark, substations 36 and 38 compensate automatically. The track never stops working. Thermal management nearly killed the project on paper before a single weld was made. The lunar surface swings from 120 degrees Celsius in direct sunlight to negative 173 in shadow. That is a delta of almost 300 degrees, and it happens every 14 Earth days as the Moon rotates. Metal expands and contracts. Over 1,000 kilometers of rail, unmanaged thermal cycling would warp the track into uselessness within 6 months. The solution is a multi-layer thermal blanket draped over the entire rail assembly, a sandwich of aluminized kapton, aerogel micropanels, and a radiator mesh that bleeds excess heat into space. Beneath the blanket, the rail temperature stays within a 9-degree window year-round. Additionally, every 12 meters, an expansion joint allows microscopic movement, enough to absorb thermal stress, not enough to break alignment. These joints are the most tested component in the entire system. Over 600 prototypes were cycled through simulated lunar thermal extremes at NASA's Glenn Research Center before a final design was approved. 600 versions of a 12-centimeter joint. That is how seriously they take the tolerances. At kilometer 412, the track crosses a rill, a collapsed lava tube that left a canyon 90 meters wide and 30 meters deep, slicing across the path. The track cannot go around it. The equatorial corridor is locked, so they bridge it. But this is not an earth bridge. There are no concrete pillars driven into bedrock. Instead, a prefabricated truss arch, manufactured in orbit at the Lunar Gateway Station and landed in 3 sections by autonomous cargo landers, is assembled by a team of teleoperated robots. The arch spans the full 90 meters, resting on sintered abutments carved into the rill's walls. The rail runs across the top of the arch, and the magnetic sled will cross this gap at over 1,000 kilometers per hour, without ever knowing it left solid ground. The engineering team calls this segment the throat. Every other problem on the project is manageable. The throat is the one that keeps them awake at night because a 90-meter unsupported span vibrating under electromagnetic pulse loads in a vacuum with 300-degree thermal cycling is not a solved problem. It is a problem they are solving in real time, testing scale models in vacuum chambers on Earth, while the Foundation crawlers on the Moon creep closer to kilometer 412 by the day.
NASA's blueprint for a lunar launch track is about to change everything. This is just the beginning.
Power for the full operational track requires approximately 400 megawatts sustained during a launch window. No single solar installation on the Moon produces that. The solution is a dedicated nuclear fission reactor, a scaled-up kilopower unit planted 5 kilometers from Base Camp Meridian, shielded by a berm of regolith 15 meters thick. The reactor core uses highly enriched uranium-235 fuel pins surrounded by a beryllium oxide reflector. Heat is converted to electricity by Stirling engines. No turbines, no steam, no water. Just pistons cycling on thermal differential. The reactor runs for 12 years without refueling, producing a steady 450 megawatts, enough to power the track, Meridian, all 52 substations, and still have a reserve margin for emergency systems. A second identical reactor is landed and installed as a cold backup before the track is declared operational. Redundancy is not optional when your power source is 240,000 miles from the nearest repair shop. The cargo sled itself is deceptively simple. A flat rectangular platform, 4 meters by 6 meters, with superconducting magnet arrays on its underside and a payload cradle on top. It carries no engine, no fuel, no moving parts beyond the latch clamps that grip the cargo pod. It is, in essence, a magnetic surfboard. The cargo pod sits on top, locked down, and the entire assembly is placed at the track's origin point, kilometer 0. Launch sequence initiation sends a cascade signal down the power trunk. The coils energize in sequence. The sled lifts off the rail surface by 6 millimeters and begins to move, slowly at first. Walking speed at kilometer 1, bicycle speed at kilometer 5, highway speed at kilometer 19. By kilometer 200, it is moving faster than any bullet fired from any gun ever made on Earth. The acceleration is constant, relentless, and perfectly smooth. No turbulence, no vibration, no atmospheric drag, because there is no atmosphere. The sled and its cargo cross the throat at kilometer 412 in less than a third of a second. By kilometer 800, the electromagnetic pulse frequency in the coils is cycling so fast that the power draw spikes to 380 megawatts. And then, at kilometer 1012, the rail ends. The sled crosses the terminal ramp, a slight upward curve calculated to an exit angle of 6 degrees above the lunar horizon, and the cargo pod detaches. It is moving at 2.4 kilometers per second. It is in orbit. No fire, no exhaust, no explosion. Just silence and velocity. The sled, now unburdened, is decelerated by reversing the coil sequence over a 4-kilometer braking runoff and towed back to kilometer 0 for the next launch.
With this launch completed and the sled turned around, we've cut our operational time in half, ensuring maximum efficiency for the lunar infrastructure.
Turnaround time, 96 minutes. The first operational launch sends a 40-ton cargo pod loaded with processed lunar aluminum and titanium ingots to the Lunar Gateway Station in a near-rectilinear halo orbit. Travel time, 11 hours. Cost of launch propellant, 0. The second launch, 16 hours later, sends oxygen canisters. The third sends prefabricated habitat panels bound for a Mars transit vehicle being assembled at Gateway. Within the first operational year, the track completes over 2,000 launches. The cumulative mass delivered to orbit exceeds 70,000 tons, more than humanity launched from Earth in the entire first 60 years of spaceflight combined. The cost per kilogram to lunar orbit drops from approximately $54,000 using chemical rockets to roughly $8 using the mass driver, accounting for amortized construction and maintenance costs over a 20-year operational window. $8. A kilogram of cargo to orbit for less than the price of a sandwich. And that changes everything. Mars missions no longer require monstrous rockets assembled in Earth orbit at staggering cost. The fuel, the water, the building materials, the radiation shielding, all of it is manufactured on the Moon from lunar resources and flung to the assembly point by a track that runs on sunlight and uranium. A crude Mars vehicle that would have taken 9 years and $300 billion to build and fuel from Earth can now be assembled in 14 months using lunar-launched materials at a fraction of the cost. The moon stops being a destination. It becomes a shipyard. The launch track stops being an engineering project. It becomes the first piece of permanent industrial infrastructure ever built on another world. A railroad that does not connect two cities but two futures. The one where humanity stays fragile and earthbound, and the one where it does not.
With this turnaround, we've revolutionized space transport. Kilometer Zero is now the fastest gateway to the stars.